Hello, hi, welcome back. Welcome back to EDUHUNT IIT and NEET foundation classes. This is Sukumar, your chemistry mentor. In the previous class, we just completed the concept called resonance. I hope you understand it very well. Now, in this particular video, I am going to start the concept called dipole moment. The concept called dipole moment. To understand this topic, the dipole moment, we just need a small concept called, first of all, what is polarity? Polarity. Now just try to understand what is polarity, then obviously we are going to discuss what is dipole moment. See, you know very well the covalent bond concept. Between any two atoms, you know very well what is the covalent bond concept. For suppose, if A is an atom and it is one of its valence electron, consider the dot as one of its valence electron, and for now I am taking another atom A, that means I am taking two similar atoms. Now imagine if these two atoms are going to share that electron pair. If these two atoms are going to share this electron pair, now obviously you can call this as shared electron pair. Shared electron pair. Okay, fine. Shared electron pair. And that shared electron pair is nothing but covalent bond, you know. So that is nothing but covalent bond. So every time, instead of showing that shared electron pair as a dots, we in general show that covalent bond as a line. That is, you have to consider this line as a pair of electron. This is a bond pair, one electron from this atom and another electron from this atom. Fine, shared electron pair. Okay, now what it means? That means this electron pair is shared equally by the two atoms. Actually, you know that in this pair, both the atoms have their equal contribution. How this pair is formed? One electron contributed by this atom and another electron contributed by this atom. Actually, this pair is formed by the contribution of both atoms, and now this pair is shared equally by the both atoms. Why? Why? The electron pair is equally shared between the two atoms. And if you ask why, there is very fundamental reason, because both are of same type of atoms. Their nuclear charge, both are A atoms only, na? So their nuclear charge, their electronegativity, everything are same. Both atoms, you can write this point as a reason, then that will be good. Why? I said the electron pair is equally shared between the two atoms. Now why? Why? Because both the atoms has same nuclear charge. It means both the atoms has the same electronegativity. Both the atoms has the same electronegativity. Please notice I am writing electronegativity as EM. So I hope you remember what is electronegativity. Electronegativity is the tendency. It is the tendency. I'll repeat. Electronegativity is the tendency of an atom to attract the shared pair towards itself. See, this atom is attracting this electron pair and that atom also attracting this electron pair, And the ability of an atom or the tendency of an atom to attract this shared pair towards itself is nothing but electronegativity. Now it is very clear that two atoms are of same type, that's why both are having same electronegativity. The force with which this atom is attracting is same as the force with which that atom is attracting. So obviously this pair is equally shared between the two atoms. Okay, the only reason is both atoms are of same type. So this is this kind of situation. You can see covalent bond between I'll say when covalent bond between similar atoms, covalent bond between similar atoms. This is the situation when covalent bond is present between similar atoms. Now question arises, sir, what if there is a covalent bond between dissimilar atoms? Obviously you can think, you can guess before I explain. When the atoms are of different type, definitely electronegativity of one atom is more than the electronegativity of other atom. Why? If electronegativities are different means one must be low, another must be high. Then what happens? One atom is having more power to pull the electron pair towards itself compared to other atom. Now the situation. I'll take next page to explain that. Now, when the covalent bond, that means shared electron pair, when the covalent bond is between two dissimilar atoms, let's take atom A has contributed its own electron, atom B contributed with its own electron. See, covalent bond means shared electron pair, definitely. Whether it is atom same type or different type, every atom is going to contribute to the shared electron pair. A is contributing one electron to the shared pair, B is contributing one electron. Now these two is that means these two electrons, which is the shared electron pair, this shared electron pair is present between two dissimilar atoms. Now for the sake of explanation, let me take, if I say if electronegativity of B is greater than electronegativity of A, if electronegativity of B is greater than electronegativity of A, what happens? It means what? You tell me. Electronegativity, what is electronegativity? Electronegativity is the power, electronegativity is the ability, electronegativity is the strength with which an atom pulls the electron pair towards itself. Now I am saying that power is more for B, then obviously what happens? This pair will be more towards B and less towards A. In the previous example, both atoms are having same power to pull the electron pair towards itself. That's why this pair is at the middle position and shared by both the atoms equally. No one is getting the electron pair more or no one is less. Both are getting this electron pair equally. That means from this electron pair you can imagine 50% belongs to that one and 50% belongs to this one if it is a covalent bond. Now the situation is a bit different. Why? Of course the electron pair is in sharing, but this shared pair is a little bit more towards B and less towards A. Now you tell me, for suppose what happens if this pair if this pair completely moves towards B. It's a question I am asking you. What happens if this pair completely moves towards B? What happens? Anyway, in this pair, one electron already belongs to B. Along with this B electron, now this atom B is getting extra electron from A, right? Now in this pair, one electron belongs to B already and the extra electron came from A. Now what happens? You imagine if any atom gets extra electron from other atom, what happens? Negative charge. So instead of writing that, I'll write this as a minus. Why it is minus? In this negative charge, or in my opinion, that minus represents one electron pair. Then in this pair, one electron is belongs to B and extra electron from A. Now what's the situation of A? The situation of A you can expect correctly. How? A has lost its own electron. That means when an atom is losing electron, it will get positive charge, 1 plus 1 minus. So that's how what happens, a cation formed, anion formed. Now this kind of situation, when you expect this kind of situation, the situation in which the shared pair is not even in sharing, it is completely moved towards one atom. What is this situation? This kind of situation you can expect when electronegativity of B is very much greater than electronegativity of A. How much greater, sir? That much greater, at which sharing is not possible. Compared to the electronegativity of A, electronegativity of B is that much high, so that sharing is not possible. B is strong enough, B is capable enough to pull that electron pair completely towards it. By that what happens? Because of that, B becomes negatively charged, you call it as anion. A becomes positively charged, you call it as cation. Obviously, between cation and anion there is an invisible attraction. You call that attraction as ionic bond. You know that bond. Now here in this case, the electronegativity of B is not that much high like this. It is just high. Electronegativity of B is not that much high to pull the total pair towards itself. It's just a case where electronegativity of B is more than A, but the electron pair is still in sharing. Now it's okay. How to express that concept on paper? If the pair is completely moved towards one atom, one will get full negative charge, one will get full positive charge, full 1 unit negative charge, 1 unit positive charge. Now what happens here? The pair is not moving completely. If pair moves completely, full negative, full positive. Now it is moving partially. That arrow mark, that kind of arrow mark head, what I mean is this pair is partially moving towards B, not fully. If this pair fully moves, B will get full negative. If this pair partially moves, B will get partial negative charge. That symbol is for partial, not complete, partial. Obviously, if this pair fully moves, A will get full 1 unit positive charge. If this pair gets partially moved, then A will get a partial positive charge. That's the situation depending upon the electronegativity difference. The concept, the backbone of this concept is what kind of first of all there should be a covalent bond. In that covalent bond, the electronegativity difference between the atoms should be like that, in that range. If there is more difference, then obviously what happens? You can expect ionic bond. Okay, now by this concept, what you observe now, this molecule you call AB molecule, in this molecule there is some polarity developed. If you observe, there is some polarity developed. Now this molecule is not a normal molecule. You can call this molecule as a polar molecule. because there is some polarity developed. At one end there is a negative charge and another end there is positive charge. Polar molecule, and obviously that bond is polar bond. That bond is polar bond. Polar molecule having polar bond. You can take an example, real example, like HCl. Between hydrogen and chlorine, that's a covalent bond. In that bond, one electron contributed from hydrogen and another electron contributed from chlorine. Of course, that is the shared pair, which is supposed to be shared between the two atoms. But the point is, compared to hydrogen, chlorine is having more electronegativity, but still the electronegativity is not that much high, so that the entire pair moves towards chlorine fully. The electronegativity is just to cause some polarity. That means chlorine will get partial negative charge, partial positive charge. You can take it in one way, like see, if the electron pair is completely moving towards one atom, full negative, full positive, completely ionic, majority ionic character, it's not covalent, ionic. Here what happened? Actually there is sharing, but unequal sharing. So you can take this as a covalent bond with some percentage of ionic character. It's a covalent bond. Covalent bond having polarity means it's a covalent bond with some percentage of ionic character. Now you know what is polarity, what is polar bond and polar molecule. Now the question arises, how can we measure the polarity of a polar molecule? Students, listen carefully what I am saying. How can we measure the polarity of a polar molecule? First of all, do we really need, is there any requirement to measure the polarity? You know what is polarity, don't forget that first of all. See, I'll write once again. If AB, this is a covalent bond, and if B is more electronegative than A, that means again I am telling the same thing, so that you have to be very clear about it. Electronegativity of B greater than electronegativity of A. If B is more electronegative than A, what I said, this bond is more towards B, so that B acquires a partial negative charge and partial positive charge. Now the point is, this molecule has developed a polarity. There is a negative pole, positive pole, there is polarity. The molecule having polarity means polar molecule, and that bond is polar bond. Now how to measure the polarity? Yes, you are seeing it is having polarity, but how much polarity? How much polarity it is having? How can we measure it? If I ask you a question like that, now you can ask me another question, sir, do we really need to measure the polarity? Yes, suppose this is one molecule you are talking about. I'll take one more molecule of similar kind, that means a bond between A and C. Here also electronegativity of C is greater than electronegativity of A. Okay, fine. Like this, here also C acquires some partial negative charge. Do remember, the partial negative charge developed here is not exactly same as partial negative charge developed here. Okay? Yes. It's a different one. So partial positive charge. Now you tell me, both are polar. Okay. Both are having polar bonds. Okay. Both are polar. Both are polar bonds. Now you tell me, which one is more polar? Which one is less polar? If I ask that, which one is more polar, which one is less polar, now we need a concept to measure the polarity. ఇప్పుడు మనం పొలారిటీని కొలవాల్సిన అవసరం కూడా వచ్చింది. Then how to measure the polarity? Yes, To measure the polarity, there is a concept called dipole moment. Dipole moment. Dipole moment. And that was indicated with the symbol mu. Dipole moment was indicated with the symbol mu. Simply, by the name itself, you can understand dipole. Di means two, pole means, yes, a negative pole, a positive pole. Dipole moment. Sir, what is dipole moment, sir? Let's define it. Let's define it. Dipole moment is the product of charge developed into distance between the poles. That means dipole moment is the product of charge on the poles into distance between the poles. But here one thing is must. Here I have expressed charge as a partial delta symbol. The point is, I hope you understood this one. The negative charge, whether it is small charge or big charge, the negative charge present on this atom is the same as the positive charge. That means the magnitude of negative charge developed here is equal to the magnitude of positive charge developed here. The same amount of charge developed here and here. Only thing is here that charge is in negative, here it is positive. So if Q amount of positive charge developed here, the same Q amount of negative charge developed here, that is we have taken here Q. Now coming to the case of units, in SI system, unit must be from the charge unit into distance unit. Charge unit into distance unit. In SI system, unit, or I can say this dipole moment, is measured in units called dBi. The unit for dipole moment is dBi. Okay, and you can simply indicate with the letter capital D. Sir, what is dBi, sir? What is dBi? 1 dBi is equal to 10 to the power of 18 erg second unit ESU centimeters. Why? This is in CGS system. You know very well, in CGS system, charge is measured in the unit erg second units and distance in centimeter. Now the same 1 dBi in SI system equal to 3.33 into 10 to the power of minus 30 Coulomb meters in SI system. I hope you understood this one. Okay. So the unit for dipole moment is the charge unit into distance unit. And in CGS system it is expressed as, see, the unit for dipole moment is dBi. In CGS system 1 dBi is equal to 10 power 18 ESU centimeter. In the same value in SI system is 3.33 into 10 power minus 30. Anyhow, what is this? This is dipole moment. What is the purpose of measuring dipole moment? If the molecule is having some dipole moment, it means the molecule is polar. If the molecule is having some dipole moment, it means the molecule is polar. And if the molecule's dipole moment comes out to be 0, non-polar. Simply you can take it like this. If dipole moment is equal to 0, then the molecule is said to be non-polar molecule. And if the dipole moment is not equal to 0, the molecule is polar. And to identify the molecule as polar or non-polar is simple in this kind of bond. That means only one polar bond. Now the concept comes, if there is more than one polar bond, In the molecule or ion, let me tell you, in the molecule or ion, if there is more than one polar bond, now please remember this dipole moment is it's a vector quantity. Vector quantity, that means dipole moment value has both, it has a magnitude and direction. Then what happens, sir, if it is vector quantity? What, sir? Yes, when there is more than one polar bond, you have to consider the net resultant dipole moment depending upon the direction of the bonds. How? You see, if there is, let us say, if there is a bond like this, AB bond, okay, now let's consider just like this, B is more polar, that means B is more electronegative than A, then simply the dipole moment is from A to B, that's okay, just like this, dipole moment is from A to B, but in this direction, that means in this direction. Now how to show that? There is a way, there is a method to express dipole moment, not like this. In general, we are going to write these partial symbols, but officially dipole moment is expressed like this. That means from from less electronegative atom towards more electronegative atom. So this arrow mark represents the molecule, this arrow mark represents the dipole moment. The dipole moment is in this direction. Now for this bond, the dipole moment is in this direction, and for this bond, dipole moment is in this direction. Okay, if you are talking about this bond, it is polar bond, it is have polarity. If you are talking about this bond, yes, polar. But the point is, for overall molecule, what is the dipole moment? Yes, the dipole moment of this bond, you can call it as mu1, and the dipole moment of this bond, you can call it as mu2. And what is the resultant dipole moment or net dipole moment of the molecule? The net dipole moment of the molecule will be in this direction. This is called mu net. The dipole moment of this bond is in this direction, and for this bond it is this direction, and the net dipole moment is towards to the bottom. So always, if net dipole moment is 0, then non-polar. If net dipole moment is not equal to 0, then it is polar. Okay, so the net dipole moment is going to be 0 or not depending upon the angle between the bonds also. There is a particular angle between this, right? Yes. So when there is more than one polar bond, the resultant dipole moment is calculated by the vector addition. Resultant vector calculation, like by the formula, let me give you. For suppose, if there is a bond like this, AB, AC. Suppose, compared to A, B is more electronegative, compared to A, C is more electronegative, both are polar bonds inclined at an angle theta. Both are polar bonds inclined at an angle theta, and the dipole moment of this bond obviously in this direction, and the dipole moment of this bond in this direction. Yes, let us call the dipole moment of this bond as mu1, and the dipole moment of this bond is mu2. What happens to the resultant dipole moment? The net dipole moment will be in this direction, mu net. Then how can you calculate that net dipole moment? Resultant vector mu net is equal to root over mu1 square plus mu2 square plus 2 into mu1 mu2 cos theta. So with this formula, that means the formula used to calculate resultant vector, with this formula we can calculate whether the molecule which is having more than one polar bond is actually polar or non-polar. You tell me. I'll give you an example like CO2. Is it polar or not? SO2, is it polar or not? Yes. Now going towards the structure. You know that carbon dioxide molecule is linear. Carbon dioxide molecule is linear, and you know very well, compared to carbon, oxygen is more electronegative. Its dipole moment is in this direction, and the dipole moment of this bond is exactly in opposite direction. So the net dipole moment is going to be 0 here. The net dipole moment is going to be 0 here. So instead of having two polar bonds, CO bond is polar, but direction also matters. So the net dipole moment is 0. This molecule is non-polar. And coming to the case of SO2 molecule, yes, double bond. I hope you know the geometry of this molecule, SO2. Sulfur is having 6 electrons in its valency shell, right? And compared to sulfur, oxygen is more electronegative. Compared to sulfur, oxygen is more electronegative. The dipole moment of this bond is in this direction, dipole moment of this bond is in this direction, and net dipole moment you can say in this direction. Obviously there is a net dipole moment valid here. This molecule is polar. This molecule is polar. This molecule is non-polar. So because of the symmetry, okay. In the next video, with more examples, I'll explain how to determine whether a molecule is polar or non-polar depending upon its dipole moment and applications of dipole moment. Thank you.